Welcome to the Deep Dive. We're the show that, well, cuts through the noise and gets right to what you really need to know. And today, we're launching something pretty special, something I know a lot of you have been asking about. It's our new CSWIP 3.1 exam prep series. Yeah, our mission here is really clear. We want to help you, our listeners, get those insights, that critical knowledge you need for the CSWIP 3.1 Welding Inspector Exam. We're not about just memorizing facts. We're going to tackle key concepts using actual exam-style questions. The idea is to give you those aha moments, make things click, make it stick, but without feeling like you're drowning in information. Think of us as your study partners, maybe, helping you find those crucial bits of knowledge that count, not just for the test, but out there in the real world. Okay, let's dive straight in. First up, non-destructive testing, a big one. Here's a question. When you're considering the advantages of site radiography over, say, conventional ultrasonic inspection, which of the following applies? Is it A, a permanent record, good for detecting lamellar tearing and defect identification, or B, a permanent record produced, good for detection of all surface and subsurface defects and assessing through thickness depths of defects, maybe C, permanent record produced, good for defect identification and not as reliant upon surface preparation, or finally D, no controlled areas required on site, a permanent record produced, and good for assessing pipe wall thickness reductions due to internal corrosion. What do you think?
Right. Well, looking at those options, the one that really hits the key advantages of radiography in this comparison is C. There are some definite plus points for radiography, and these three, permanent record, defect ID, and surface prep, they really capture the main ones.
Okay, let's break that down a bit. The permanent record, why is that such a big deal compared to ultrasonics?
It's huge, actually. With radiography, you get a physical film or a digital image. It's, tangible evidence. Unlike ultrasonic testing, where the data can be, well, a bit transient unless you're meticulously recording every signal, the radiograph is a snapshot. You can archive it, review it later, use it for audits, quality checks, even track if a defect changes over time. For things like compliance or documentation, that's gold.
Right, like having actual proof you can file away.
Exactly. Then there's the defect identification aspect. Radiography often gives you a clearer picture, literally, of the defect's shape and where it sits inside the weld. You can often see porosity or the line of a crack or maybe incomplete fusion much more intuitively than interpreting the blips and signals from conventional UT, especially for certain types of flaws.
So it's more visual, easier to maybe diagnose what you're seeing.
In many cases, yes. And the third point, from SLEE's less reliance on surface preparation, this is a big practical advantage out on site. Conventional ultrasonics needs a pretty clean, smooth surface. You need good contact for the sound waves to get in properly. That often means grinding, brushing. It takes time. Radiography, well, you need access, obviously, but it's generally much more forgiving of a bit of surface roughness, maybe some light scale or paint. The rays just punch through. That can save a lot of time and hassle in the field.
Okay, that definitely paints a picture of why you'd choose radiography. But it's not always the best choice then. Thinking about those other options like lamellar tearing in A or controlled areas in D.
That's a really important point. No single NDT method is perfect for everything. So yeah, radiography has downsides too. You mentioned lamellar tearing.
Yeah, option A.
Right. While radiography can sometimes pick it up, conventional UT is often much better for detecting planar flaws like that, especially if they're oriented parallel to the surface. UT can often give you better depth information too. And option D is just plain wrong about controlled areas. Radiography uses X-rays or gamma rays, that's ionizing radiation. You absolutely need strict safety zones and controls. Major safety implications there.
Ah, okay. So safety is a big factor.
Huge. And for things like accurately measuring wall thickness loss from corrosion or pinpointing the exact depth of a flaw, ultrasonics often gives you more precise real-time data without the radiation risk. So the takeaway really is you need to know the strengths and weaknesses of each method. The skill is picking the right tool for the specific job, considering the material, the suspected defects, the site conditions, everything.
Makes perfect sense. It's about having the full toolkit and knowing when to use each piece. Okay, let's shift gears slightly. From finding flaws to ensuring the weld is right in the first place. Let's talk geometry, specifically fillet welds. This feels fundamental. Here's the question. Fillet welds. What's the ratio between the leg length and the design throat thickness on a miter fillet weld with equal leg lengths? Your options are A, 1:1, B, 2:1, C, 1.4:1, or D, all the above could be applicable. It depends upon the leg length size.
Okay, for that specific case of miter fillet, equal leg lengths, the magic number is C, 1.4:1. And this isn't just arbitrary, it comes straight from basic geometry. Pythagoras, essentially.
Okay, geometry. Walk us through that.
Sure. Imagine slicing through the weld. With equal legs and a miter shape, you've got a right-angled isosceles triangle. The two equal sides are the leg length. The design throat thickness is the shortest distance from the root corner out to the face of the weld. Basically, the height of that triangle if you stand it on its hypotenuse. Mathematically, the throat thickness works out to be the leg length times the sine or cosine of 45 degrees, which is about 0.707. So if you flip that around to find the leg length needed for a certain throat thickness, you divide by 0.707, which is the same as multiplying by roughly 1.414, hence the 1.41 ratio. For every 1 unit of throat, you need about 1.4 units of leg.
Right, that's quite precise. So for an inspector checking welds, how critical is hitting that exact 1.4 ratio? What happens if it's a bit off? Is there a common mistake people make?
It's actually very critical. The insight here isn't just the number, but what it represents. Strength. Engineers design welds based on the throat thickness, because that's the effective area carrying the load. If your leg length measurement is off, even by a small amount, your actual throat thickness could be significantly less than required. Let's say you measure a leg length that's 1 millimeter too short on a, say, 7 millimeter leg weld. That doesn't sound like much, does it?
Not really, no.
But it translates to a throat thickness that might be around 0.7 millimeter undersized. That could mean a significant reduction, maybe 10-15%, in the weld's load-bearing capacity compared to the design intent. So the common pitfalls may be just visually checking leg length or being a bit casual with the gauge. An inspector needs to be precise because that seemingly small geometric difference directly impacts structural integrity. It could be the difference between holding and failing under load.
Wow, okay. So a tiny measurement error has potentially huge consequences. That really highlights the responsibility. Okay, sticking with the fundamentals, let's talk materials. Steel metallurgy specifically, something that can cause real problems during welding. Question: which element in steel, if present in significant amounts, may lead to hot shortness? Is it A, phosphorus, Pb, manganese, Mn, C, silicon, Si, or D, sulfur, S?
The one we're looking for there, the main culprit for hot shortness, is D, sulfur. Yes, sulfur or S. And hot shortness is exactly what it sounds like. It's when the steel becomes brittle and weak at high temperatures.
Like when you're welding it.
Precisely. During welding or even hot rolling or forging, instead of deforming nicely, it just cracks. It loses its ductility when it's hot. The reason sulfur causes this is down to chemistry. Sulfur loves to combine with iron to form iron sulfides, FAS. Now, the problem is these iron sulfides have a much lower melting point than the steel itself, and they tend to gather at the grain boundaries, the edges between the individual crystals in the steel. So when you heat the steel up during welding, these iron sulfides melt first, while the rest of the steel grains are still solid. They form thin, weak liquid films right along those grain boundaries. These liquid films basically break the connections between the grains. They can't hold any load. And under the stresses of heating and cooling during welding, the grains just pull apart along these melted boundaries. Bang, you get cracking. Hot shortness cracking.
That's fascinating. Liquid films inside seemingly solid steel causing cracks. You hear about manganese being added to counter this. How does that work? Does it completely solve the sulfur problem?
Good point. Yes, manganese Mn is key. It's added deliberately, often called a scavenger. Manganese has a higher affinity for sulfur than iron does, so it preferentially reacts with the sulfur to form manganese sulfides, MnS, instead of those nasty iron sulfides, MES.
And MnS is better.
Much better. MnS has a significantly higher melting point, much closer to that of the steel itself, so it doesn't melt prematurely. Also, MnS tends to form as small, sort of rounded, isolated particles within the grains rather than continuous films along the boundaries. These isolated particles are far less damaging to the steel's hot ductility.
So it's a balancing act then. Control the sulfur, make sure there's enough manganese.
Exactly. Steel specifications always limit sulfur content for this reason, and they ensure sufficient manganese is present. It's a great example of how metallurgists manipulate chemistry on a tiny scale to prevent major problems during fabrication and ensure the material behaves as expected, especially under the intense heat of welding. But yes, too much sulfur can still overwhelm the manganese effect.
Incredible detail. Okay, knowing the material is crucial, but so is controlling the welding process itself. Let's look at submerged arc welding, SAW, a really important industrial process. Question: in the SAW welding process, what would happen with excessive voltages? A, the use of excessive voltages would result in insufficient flux melting. B, the use of excessive voltages would result in excessive flux melting. C. The use of excessive voltages would result in easy slide removal. D. The use of excessive voltages would result in excessive spatter.
Right. Thinking about SAW parameters, the correct answer here is B. Excessive voltage leads to excessive flux melting. In SAW, the arc is buried under that layer of granular flux. Voltage is directly related to the arc length. Higher voltage means a longer arc.
Okay, longer arc. So what?
Well, a longer arc spreads the heat out over a wider area of the flux blanket beneath it. More voltage, longer arc, more heat spread over more flux. This directly causes more of the flux to melt than is ideal. You get excessive flux melting.
And why is too much melted flux a bad thing?
Several reasons. The slag becomes very fluid, maybe too runny. It might not properly shield the molten weld pool underneath from the air, leading to defects like porosity. Also, the flux often contains alloying elements that are supposed to transfer into the weld metal to give it the right properties. If you melt too much flux, you can dilute these elements, changing the weld chemistry and potentially weakening it. Plus, that longer, wider arc tends to produce a flatter, wider weld bead profile with potentially shallower penetration, which might not be what the design requires for strength.
I see. So voltage control is pretty critical for the whole process.
Yeah.
What are the visible signs an inspector might see if the voltage is too high, things you could spot immediately?
Good question. Visually, you might notice that very wide, flat bead profile I mentioned. The slag covering might also look different, perhaps very glassy or shiny, and sometimes it can be harder to remove, maybe chipping off in awkward flakes instead of peeling cleanly.
So difficult slag removal could be a clue, even though option C suggested easy removal.
Exactly. Option C is wrong. Excessive voltage often makes slag removal harder or more brittle. Easy slag removal usually comes from well-balanced parameters. And you might, if you could hear it well, notice a less stable arc sound, even though it's submerged.
And the other options? Insufficient melting and spatter.
Insufficient melting, option A, would typically be caused by too low voltage, not too high. And excessive spatter, option D, isn't really a characteristic issue in SAW because the arc is covered by the flux. That's more of a concern in open arc processes like MIG-MAG or stick welding. So it really hammers home that getting the parameters right, especially voltage in SAW, is vital for controlling the melt, the bead shape, the chemistry, and ultimately the quality of the weld.
Absolutely vital. Okay, final question. Let's tie a few of these threads together. Material properties, welding procedure, a real-world type scenario. Question. Which of the following properties might apply to a carbon steel weld with a carbon equivalent, or CE, of 0.48, which has been welded using a fast travel speed and without preheat? Would you expect? A. A narrow heat affected zone and hardness value in excess of 350 HBB. A broad heat affected zone and hardness values in excess of 350 HBC. A very tough and narrow heat affected zone. Or D. A narrow heat affected zone and low hardness values.
Okay, this one pulls together quite a bit. Given those conditions, CE of 0.48, fast travel, no preheat, the most likely outcome is A. A narrow HAZ and high hardness, likely over 350 Vickers.
Right, let's break that down. Why that combination? Start with the CE value.
Okay, CE 0.48. That tells you the steel has a relatively high carbon and/or alloy content. It's got higher hardenability. That means it's more likely to form hard, brittle structures if it cools down quickly.
More prone to getting hard.
Yeah.
Okay, now the fast travel speed.
Fast travel speed means the heat source, the arc, moves quickly. This puts less total heat into any given point along the weld seam per unit of length. Less heat input generally means the heat doesn't spread as far into the surrounding base metal. So the result is a narrower heat-affected zone, or HAZ. The zone next to the weld that got hot but didn't melt is smaller.
Narrow HAZ. Got it. And the lack of preheat.
That's the clincher. Preheat is used specifically to slow down the cooling rate after welding. If you don't use preheat, especially combined with the lower heat input from fast travel speed, the weld and the HAZ cool down very, very quickly. So you have rapid cooling acting on a steel that's prone to hardening, high CE. That's the perfect recipe for forming hard microstructures like martensite in that narrow HAZ. Hard microstructures mean high hardness readings easily exceeding 350 HAZ in this case, and unfortunately, high hardness often means low toughness, making the HAZ brittle and susceptible to cracking.
So, narrow HAZ, high hardness, potentially brittle. That sounds risky. Have you seen failures caused by exactly this kind of situation in practice?
Yeah.
Where maybe someone skipped preheat or pushed the speed too much?
Oh, absolutely. It's a classic scenario for hydrogen-induced cracking, sometimes called delayed cracking. I remember a case on a structural steel job, similar CE material. They were behind schedule, started increasing travel speeds significantly, thinking they were saving time, but didn't increase the preheat to compensate. The welds looked okay on the surface initially. Yeah. But days later, NDT found extensive cracking, mostly fine cracks, hidden in the HAZ. The combination of the susceptible material, the stress from welding, some hydrogen present, and that hard, brittle HAZ created by the fast cooling, it just couldn't handle it. It was a very expensive lesson about why procedures, especially preheat and travel speed limits for higher CE steels, exist. That's why option B is wrong, fast travel and narrow HAZ. C is wrong, high hardness is low toughness, not high. And D is wrong, high CE plus fast cooling equals high hardness, not low. It really shows how material science and procedure control are completely intertwined. You have to understand both.
Wow, what a journey through some really core concepts for welding inspectors. We've hit NDT advantages, fillet weld geometry, metallurgy quirks like hot shortness, SAW process control, and tied it all together with weldability and HAZ properties. That was quite the deep dive.
It really was. And hopefully what comes across is that it's not just about knowing the right answer for an exam question. It's about understanding the why behind it. Why does sulfur cause hot shortness? Why is that 1.4 ratio important? How do voltage and travel speed actually affect the metal? That deeper understanding is what makes a good inspector, being able to apply these principles in real situations. It's critical thinking, not just memorizing.
Absolutely. That critical thinking piece is key. So as you, our listener, continue prepping for the CSWIP 3.1, maybe mull this over. How do all these seemingly separate details, the geometry, the chemistry, the process parameters, all link together to ensure the safety and integrity of the final structure? What's the single biggest insight you took away from our discussion today that you'll use next time you're studying or inspecting a weld? Thank you so much for joining us on the Deep Dive today. Keep digging deeper, keep asking questions, and we'll catch you on the next one for more CSWIP prep.